And this is my Physics Lab 5 Falling Slinky. Introduction. So for this lab, we were basically supposed to choose one type of physics thing to observe or do an experiment with, and I just chose the example at the bottom of the options for examples that was about a slinky that is let go at static equilibrium and then comes all the way down to the rest of the slinky and then falls by itself to the ground. So for the preview of results, you can see that in the graph, the computational model followed the real life slinky pretty well with this portion and this portion. And basically my goal with this was just trying to create a computational model that would follow the motion of the tracker data. So for this, the physics concepts were basically Newton's second law with force equals mass times acceleration, and the force of gravity, mass times acceleration due to gravity, then the velocity update formula, the position update formula, and then drag force. As shown by these free body diagrams, this is the before state, before the slinky gets to the bottom, fully compressed. And this is showing that the gravity, the force due to the gravity and the tension in the slinky, because it is basically just a really big spring, were equal, which was why the bottom of the slinky wasn't moving. But then, once the compression is complete, it leaves us with just gravity and drag. So here's what the tracker video looked like. Yeah, so as shown there, you can see that the slinky falls, but it doesn't move until it gets all the way to the very compressed state. And this is what the graph looked like on the tracker data, which is then moved to my Excel spreadsheet graph, which you see in the results. So for the coding for this, basically I used the starter code from lab 2, which was where we just dropped a light object and made a computational model with the drag and force of gravity. So for this, I had the mass of the slinky, which I found online, just looked up how much does the slinky weigh. The initial position, which, because I'm bad at using tracker, was a little off, 0, 0, 0, but the time based on the tracker time, the gravity due to acceleration, then the B value for my drag, which I found by trial and error. Along with this, we have the tension and the gravity forces for the time until it reaches the bottom, the full compression, which that is just the mass times gravity. Then over here, mass times gravity, and then the drag force once it's after the compression. So finally, for the results, this is what the graph looked like for the observed and experimental. So basically, the observed is the blue, and then that's supposed to say computational, but the computational is the orange. And so putting them next to each other, you can see that this entire part right here is very, very accurate. And then when we get this way, it follows the same motion to a degree. Obviously, I think there were many errors in this, with me just being really bad at doing tracker, clicking on the right correct spot. And then also the B value for the computation model might be slightly off, just because that was found by trial and error and then figuring out what matched best. So finally, for the what does it mean question, does the bottom of the model slinky stay stationary just like the video? Yes, it does. So basically, as seen here, this line where they're almost perfectly equal, except for this front mess up that I had, they're basically exactly the same. So as I was saying before, this is due to the fact that the slinky, which acts like a spring, has that tension force in it because it's at its relaxed length, and then it comes all the way down to compressed. And once it's all the way compressed, gravity takes over and is greater than the tension that was once there. So yeah, so that's what it means. So thank you for watching.